Let's start talking about the basics of quantum computing. And I mentioned in the earlier video about a qubit, but a qubit is the smallest piece of information, but it's a huge amount of information. And the example I'm going to use is an ion. An ion is an atom with one or more electrons missing so that it has a unbalanced charge. And that unbalanced charge is useful because you can move the ion with magnetic fields, and then you can trap it and hold it and actually use a single ion. Now this is a good example because a single ion has a lot of information in just its very fundamental energy levels. So let's think about that. Fundamental energy levels, and you could say, well, let's just put it at the lowest energy level and measure what that is. Here's the problem, is prior to our measurement, the equation that defines what's going on in that energy level is very complicated, and it involves not just the lowest but the next one up. So it's a superposition which showed up in that first video. That superposition shows us the whole state of what's going on. And that whole state of what's going on goes all the way back to the fundamentals of quantum mechanics, quantum mechanics, with Schrodinger's equation, or Schrodinger's equation. I always have trouble pronouncing it correctly. But anyway, that equation shows all the different states that exist. And in this video, I'm going to get to the point where we can show a geometric representation of all the states of a qubit that occurs between a 0 level and a 1 level. In this case, a 0 level indicates the lowest energy, and a 1 indicates the next energy level up. And those are just labels. 0 level doesn't mean 0 energy. It's still an energy level. And 1 doesn't necessarily mean have anything to do with 1. We're just using 0 and 1 as labels, which are the same as what you do with bits. So let's get into the really bad stuff when we talk with equations and numbers. So that's where we're going next. Okay, you ready? Schrodinger's equation, fundamental to quantum mechanics. And you notice if you take out this IH thing, then it looks just like a first order differential equation. First partial of this function, it's not a partial because it's just a function of t, but the first derivative of this function equals, that's supposed to be an equals sign. It's really dim there, but it's supposed to be an equals sign, and that's the Hamiltonian, which is the total energy operator, and then here's the function. So it's the function, take the first derivative, you get that function back times a constant. Now what does that sound like? That sounds like the solution is going to be the logarithm thing, that e to the something. E to the something, you take the first derivative, you get e to the something right back again. So that's what we're doing there. Now, where are we going to go next? Okay, we want two different energies. So what we're doing is we're defining what this function is right here. And we're defining it in terms of two things, a 0 and a 1. Oh, now we're going to the qubits. So here's the function, here's the function with respect to time for the 0 and function with respect to time for the 1. And this 0 is represented by a column vector 1 over 0, and this is represented by a column vector 0 over 1. So those two things are orthogonal because they don't, you take the inner product of those two and you get 0. Okay, let's keep moving along here. So, if we're only dealing with two energy levels, this is supposed to be an equal sign. I don't know why it doesn't show up very well as it's rendered here, but the Hamiltonian for the ion that's not being messed with at all is just the energy times these two things multiplied together. Here's the ket vector and the bra vector, bracket, get it? And here's the ket vector and the bra thing of that. And what this will do is it'll create a matrix, not a number, but it'll create a matrix which is 1, 0, 0, 0, and it'll just select out this E0 energy. This one, in contrast, will select out will give us a matrix that looks like 0, 0, 0, 1. And that 1 will select that E1 energy. Are we on track? Now, I'm going to back up here a little bit. Remember, here's the function that we're talking about. And come down here and, whoa, did we get a solution? Whoa, look at that. We went to a solution just zippity zap real fast. Here's the E sub 0. Here's the E sub 1. And let's see what else we got here. Okay, here's the solution that I talked about. The first order differential equation that we solved for this. This one has an E0 in the exponent. This one has an E1 in the exponent. And if we factor out this E sub 0, we'll get an E sub 1 minus E sub 0 up here, which demonstrates what it's showing here as the relative phase. So this is if we're not doing anything, and it'll just pretty much remain in the 0 state. At time 0, this one is a 1, and at time 0, this is a 0. So the upper energy doesn't show up, the lower energy does show up, and that's pretty much the way it stays. Now, if we want to do something with this, apply a gate to the qubit where we're going to combine it with multiple operations, which if we don't, we're really not doing quantum computing at all. If I move down here a little bit, now we're applying a laser field, and it gets really messy. And you'll see some specific things in this equation. That's supposed to be an equal sign again. It doesn't show up much while I'm recording it. So this RWA Hamiltonian, remember the last one had a sub-0 there. That was with just the bare ion with no lasers involved. The laser couples the two states via a Rabi interaction. Whoa, Rabi interaction. Anyway, it has to do with frequencies. You'll notice the delta here is the omega minus omega 0 is the detuning. Here's the omega from the laser itself. This is the resonant frequency. So we've got a little bit of difference between those two. And that allows the qubit to do some transitioning. And it leaves it in a state where it can move between the 0 and the 1 energy. Now this omega here is the Rabi frequency, and that frequency is proportional to the field strength. Now one thing I guess I should check is the Rabi frequency and the laser frequency the same thing? Not sure. Okay, here we go. X and Z are the Pauli matrices. So these are 2 by 2 matrices that are constructed this way. Okay, that's going to give us a little different result. Then we add it to this thing, which is going to give us a result. Now, this is going to be a matrix output. And what will that matrix output be? As we look at this setup here, we have to figure out what these matrices are, and we also are going to add these matrices down here. If you look at this one, maybe we'll look at this first and kind of straighten stuff out. But if you factor out h over 2, it's actually h bar. Is that h bar? Yeah, that's h bar over 2. Pull that out of here. That's understandable. But this is not so obvious that we come up with this. Here's the result of the X matrix and the condition of the Z matrix. And then I have a delta Z, and all I did was just take the Z matrix and multiply each element times Z. So you come up with that. Then I take the omega and multiply times X, and then you come up with the omega X equals that value here. If we have the delta Z plus the omega X, that gives us the delta omega omega minus delta. And if you see here, this is the vector for this is for the 0 function, and this is for the 1 function. And then we have this arrangement here, and we factor that out. So when we get this all done, this becomes the Schroedinger equation with just these 2 qubit states. Let's talk about how you can trap an ion. How do you trap an ion? Well, you can put some bars together, and I've got my fingers up here to represent the bars of what they call a quadrupole. And this quadrupole has frequencies running through it such that if I put an ion in the middle of that quadrupole, it will respond to the magnetic fields. Just because it's a charged ion. And it can be charged such that we can create with RF frequencies a little place where we can kind of levitate that ion in between those poles. So there's a certain frequency that has to go on to levitate into those poles. Now, once we've got this ion stuck there, that ion itself has its own resonant frequency, so it acts like it's on a little spring in the middle of those quadrupoles. So that's a little frequency that has to go on. And we have yet to analyze that with the Schroedinger equation. So think of it this way. What we have not analyzed is this little ion running around at a frequency which is a little different than the RF frequencies that's levitating it, and we want to look at that as a harmonic oscillator. So we'll look at a equation that talks about that as a harmonic oscillator. Then once we get that harmonic oscillator thing figured out, then we can look at what happens to the energy states of that ion. And that's what we've been talking more about so far. But I overlooked the fact that we have to talk about how that thing actually vibrates there in that quadrupole, which are these 4 bars that hold that ion in the middle of that.